Have you ever just stopped and thought about, what's inside everything around you? Like your phone, the chair you're sitting on, even the air. It's all made of the same basic bits and pieces. But how those pieces fit together, and maybe more importantly, how we pull them apart, that's a huge story. It actually affects your life every single day.
It's pretty amazing when you think about the organization, isn't it?
Yeah.
So for this deep dive, we're going to sort of peel back those layers. We want to understand the fundamental ways we categorize all matter: elements, compounds, and mixtures.
Right. Our mission today is really to sift through all the info, figure out what really makes these things different, and maybe uncover why taking them apart isn't just some lab experiment. It's something you rely on constantly, often without even, thinking about it. And we found some, pretty surprising facts and really clever techniques to share, all drawn from some core chemistry sources we've been looking at.
Yeah, some foundational stuff.
So, okay, if we're going to try and make sense of the literally millions of different substances out there, from steel in a bridge to the air in your lungs, where do we start? What's the first big classification?
Well, the first major split, the sort of top-level view, divides everything into either pure substances or impure substances.
Okay, pure and impure. What makes something pure in this context?
So a pure substance is all about consistency. Every single particle is identical. That means it has definite, unchanging properties like a very specific boiling point, melting point, or density that never changes.
So it's uniform through and through.
Exactly, homogeneous. Its composition is the same everywhere within it. And importantly, this category includes both elements and compounds. We'll get into those specifics in a bit.
Okay, pure means consistent, uniform. Elements and compounds. But like you said, there's the other side. The world's full of, stuff that's not perfectly uniform, right? Which brings us to the impure ones.
Precisely. Those are the impure substances, and really that's just another way of saying mixtures.
Okay. So impure equals mixture.
Yep. Impure substances, or mixtures, are made up of two or more pure substances. Could be elements, could be compounds, could be both, that are just physically mixed together. And they can be mixed in any proportion.
Any proportion.
Any proportion. And the crucial point here is they don't undergo a chemical change when mixed. So they don't develop a completely new set of properties. Instead, they mostly just keep the individual characteristics of whatever you mix together.
So like if you mix sand and sugar, you still have sand and you still have sugar. They haven't become something totally new.
Exactly that. Or think about the air we breathe. It's a mix of nitrogen, oxygen, argon, carbon dioxide, a bit of water vapor, maybe some dust. Each of those gases pretty much keeps its own properties within that mix. That's a classic mixture. Sugar solution, sand, and stones. Those are all everyday examples.
Got it. Pure substances are uniform elements or compounds. Impure substances are mixtures where things are just blended and keep their original traits. Okay, let's unpack the pure ones first. Elements. We hear that word all the time. What is an element at its absolute core? You said they're pure.
Right. An element is the simplest form of a pure substance. The key definition is that it cannot be converted into anything simpler by any ordinary physical or chemical process.
What does ordinary process mean here? Like you can't just boil it down into something else.
Exactly. You can't heat it, cool it, zap it with electricity in the usual way, or react it with common chemicals and expect it to break down into different, simpler substances. Each element has its own totally unique set of properties.
And why is that? What makes them unique?
Because they're made up of extremely small particles called atoms. And here's the critical part. All the atoms within one element are identical to each other, but they are fundamentally different from the atoms of any other element.
So an atom of gold is different from an atom of oxygen.
Completely different. Different internal structure, different number of protons, mainly. That's what defines the element and dictates its properties.
Yeah.
An aluminum atom just behaves differently than an oxygen atom because it is different at that fundamental atomic level.
That makes sense. It's all about the atoms. Now, this idea of an element, it feels foundational now, but has it always been understood this way?
Not exactly in the modern sense. People, alchemists and early thinkers wrestled with fundamental substances for centuries. But it was Robert Boyle, back in 1661, who first used the term element in a way that starts to look scientific.
Boyle, okay.
But the really useful, experimentally grounded definition came later from Antoine Laurent Lavoisier, the famous French chemist around the late 1700s. He basically said, if you can't break it down experimentally, then it's an element. And that idea really paved the way for modern chemistry.
Lavoisier, got it. And how many do we know of now?
Today, we officially recognize 118 elements. Most of those, 92, occur naturally on Earth. The others have been created synthetically in labs.
Wow, 118 building blocks for everything. What's fascinating, as you said, is how these abstract things show up everywhere, in us, in everyday objects. How do scientists group them based on how they behave?
Yeah, based on their properties, we generally classify elements into 4 main groups. First, you have the metals.
Like iron, gold, copper, the obvious ones.
Those are the classic examples, yes. Metals actually make up the vast majority of the known elements. Yeah, but they show up in surprising places, too. Did you know calcium, a metal, is essential for your bones and teeth? It's in chalk, too.
Right. Calcium. I knew that was important.
And magnesium, another metal, is right at the heart of chlorophyll, the molecule that lets plants capture sunlight for photosynthesis.
No way.
Yep. And iron, of course, is crucial in your hemoglobin, carrying oxygen in your blood.
Yeah.
Even the aluminum foil wrapping your chocolate bar, that's a metal doing its job.
So metals are everywhere, often hidden in plain sight. What are the other groups?
Then you have the nonmetals. There are fewer of these. Think hydrogen, oxygen, carbon, nitrogen, chlorine, sulfur. Many are essential for life.
Okay, metals and nonmetals. That seems like a big divide.
It is, but there's an in-between group called metalloids. These show properties of both metals and nonmetals. Boron, silicon, germanium, arsenic. They're kind of hybrids. Silicon, for instance, is hugely important in semiconductors for electronics.
Ah, the computer chip element.
Exactly. And the final group is the noble gases, or sometimes called inert gases. Helium, neon, argon, krypton, xenon, radon. Their defining feature is that they are extremely unreactive chemically. They generally don't like to combine with other elements.
Like party poopers of the chemical world.
Huh. You could say that. They're very stable on their own.
That's a neat classification. Now, speaking of elements, the periodic table, it's full of these 1 or 2 letter codes. Some make sense, like O for oxygen, H for hydrogen. But then you see Q for copper, and A for sodium, Fe for iron. Why the weird ones? It seems a bit random if you don't know the code.
It does seem odd at first glance, but there's a system approved by IUPAC that's the International Union of Pure and Applied Chemistry. It's a universal shorthand.
Okay, so there are rules.
Yes. Rule 1. Often, it's just the first letter of the English name, capitalized.
Yeah.
Like you said, O for oxygen, H for hydrogen, C for carbon.
Simple enough.
Rule 2. If the first letter is already taken, you use 2 letters. The first is always capitalized, the second is always lowercase. So hydrogen is H, but helium needs 2 letters, so it's he.
HVS he. Got it.
Same for boron, B, versus bromine, BR, or barium, Bay.
Yeah.
The second letter isn't always the second letter of the name, though. It can be another prominent letter.
Yeah.
Like carbon is C, calcium is K, but chlorine is Cl.
Okay, first letter or first plus another letter makes sense. But what about copper, Cu, and sodium? They don't fit that pattern.
Right. That's rule 3, essentially. Some symbols come from the element's older name, often Latin or Greek. It's a nod to history. Copper's symbol, Q, comes from the Latin word cuprum.
Ah, cuprum.
Sodium's Na comes from natrium. Iron's Fe is from ferrum. Gold's O is from aurum. Silver's Ag from argentum. Potassium's K from calcium.
So it's a mix of English first letters and these historical Latin or Greek roots. Kind of a chemical code. Okay, that clarifies the symbols. Now let's move on. Elements are the basic building blocks. How do they combine to make something new? What exactly is a compound?
So a compound is also a pure substance, remember, just like an element.
Yeah.
But it's formed when 2 or more different elements combine chemically.
Chemically, that's the key word.
Absolutely key. They combine in a fixed ratio by mass. You can't just mix any amount. The proportions are precise. And the smallest particle of compound that still has the compound's properties is called a molecule.
Okay, fixed ratio, chemical combination, molecules. What are some common examples?
Water is the classic 1H0. 2 hydrogen atoms chemically bonded to 1 oxygen atom, always in that ratio. Common table salt, sodium chloride, NaCl is another. Sugar, like sucrose, carbon dioxide, COO. These are all compounds you encounter daily.
Okay, here's where my mind gets a little blown, and I think it does for many people. You just said salt is sodium chloride, made from sodium and chlorine.
That's right.
But wait, sodium on its own, that's a metal. It's super reactive, explodes in water, pretty dangerous stuff. And chlorine, that's a greenish, poisonous gas. How can you put those two together and get, well, salt, something we sprinkle on our food? How are compounds so drastically different from the elements they're made of?
That is the single most fascinating and defining characteristic of compounds. You've nailed it. The properties of a compound are entirely different from the properties of the elements that make it up.
Entirely different, not just a blend.
Not even close to a blend. It's a complete transformation. When elements combine chemically to form a compound, their atoms actually rearrange. They form new chemical bonds, their electrons get redistributed. It's a fundamental change at the atomic level.
Yeah.
This chemical reaction creates a brand new substance with its own unique set of properties.
So the sodiumness and the chlorineness just disappear.
In terms of their original dangerous properties, yes. The highly reactive, soft, silvery sodium metal and the toxic greenish-yellow chlorine gas react chemically, and it often involves energy release to form sodium chloride. White, crystalline, stable, essential for life, completely safe to eat. It's a chemical rebirth.
Wow. That's incredible. So the chemical bond is everything. What are other key traits of compounds then, besides this radical property change?
We'll link to that. Compounds can only be broken down into their constituent elements by chemical means. You can't just physically separate them like you might with a mixture.
So you can't just filter the sodium out of salt water?
Nope. You need a chemical reaction.
Okay.
Like with water, H2O, you can use electrolysis, passing an electric current through it to break the chemical bonds and get back hydrogen gas and oxygen gas. That takes energy in specific chemical conditions.
Okay, chemical breakdown only. What else?
We mentioned the fixed composition. The elements are always present in the same ratio by mass. Water is always roughly 89% oxygen and 11% hydrogen by mass. Also, energy is usually either absorbed or released when a compound is formed, that sodium and chlorine reaction. It gives off heat and light. And finally, every compound can be represented by a definite chemical formula like H2O or NaCl, which shows exactly which elements are in it and in what ratio.
Fixed ratio, chemical bonds, new properties, chemical separation only, energy change, definite formula.
Got it. So that's compounds. Now let's contrast that directly with mixtures. How are substances put together in a mixture if it's not a chemical transformation?
Right. A mixture, remember, is an impure substance. It's formed when you just physically mix two or more pure substances together. These substances can be elements or compounds or a mix of both. And critically, they can be mixed in any proportion.
Any proportion, unlike compounds.
Exactly. And the absolute key difference, in a mixture, the substances do not undergo any chemical change. There's no reaction, no new bonds formed between the different types of particles. So they just hang out together.
Pretty much. They're just physically mingled. And because there's no chemical change, the components retain their individual properties. Think about air again. Oxygen in the air still behaves like oxygen. Nitrogen still behaves like nitrogen. They're just mixed.
Okay, that distinction seems clear in theory. But if I'm just looking at something, maybe a powder or a liquid, how can I definitively tell if it's a compound, chemically bonded new properties, or a mixture, physically blended original properties? What are the dead giveaways for a mixture?
There are several telltale signs. First, because the components are just loosely held together without any real chemical force between them, no new substance is formed. This means, as we said, they keep their individual properties.
Like your salt and chili powder example earlier.
Exactly. If you mix salt and chili powder, the mixture tastes both salty and hot. The individual components haven't changed. Mix salt and sugar, it tastes salty and sweet. The properties are just combined, not transformed.
Okay, retaining properties is clue number one. What else?
Second, mixtures don't have a fixed composition. The proportions can vary widely. You can add a little bit of sugar to water or a whole lot of sugar. Both are sugar-water mixtures, just with different levels of sweetness. The ratio isn't fixed like it is for a compound.
Variable proportions, check.
Third, and this is a big practical difference, the components of a mixture can usually be separated by simple physical methods. Because they aren't chemically bonded, you can often use techniques that rely on differences in their physical properties.
Like?
Evaporating the water from a salt solution to get the salt back. Or filtering sand out of water. Or using a magnet to pull iron filings out of sand. These are physical separations, not chemical reactions.
That makes sense. You can't easily filter the sodium out of salt, but you can filter sand out of water.
Precisely. Fourth, the melting and boiling points of mixtures are generally not fixed or sharp like they are for pure compounds. They often melt or boil over a range of temperatures, and the exact temperature depends on the proportions of the components. Pure water boils exactly at 100 degrees Celsius at standard pressure, but salt water boils at a slightly higher temperature, and the more salt you add, the higher the boiling point goes.
Ah, so fuzzy melting boiling points are a sign of a mixture?
Often, yes.
Yeah.
Fifth, usually no significant energy change like heat being given off or absorbed happens when you just mix things together. Forming compounds often involves energy changes, but just stirring sugar into water doesn't really release or absorb much heat.
Okay.
And finally, because their composition isn't fixed, mixtures can't be represented by a single, definite chemical formula like HAO or NaCl.
No formula. Got it. That's a good set of distinguishing features. You mentioned a really great activity earlier, comparing an iron-sulfur mixture to an iron sulfide compound. Can you walk us through that? It sounds like it perfectly illustrates these differences.
It's a classic, yeah. So imagine you take some iron filings, little bits of iron metal, and some yellow sulfur powder, and you just mix them together in a dish. That's your mixture.
Okay, just physically stirred together.
Right. Now, test its properties. If you bring a magnet near this mixture, what happens?
The iron filings should stick to the magnet, right? Because iron is magnetic.
Exactly. The iron retains its magnetic property. Now, take a bit of the mixture and add some carbon disulfide, which is a solvent. Sulfur dissolves in carbon disulfide, but iron doesn't. So the sulfur will dissolve, leaving the iron behind.
Okay, so the sulfur also kept its property of being soluble in that specific solvent.
Correct. The magnet test and the solubility test show that both iron and sulfur kept their original individual properties in the mixture. And you could, in theory, separate them using these properties: magnet for the iron, solvent for the sulfur.
Clear signs of a mixture. Now, what happens if you make the compound?
Now, take that same mixture of iron and sulfur, put it in a test tube, and heat it strongly. They react chemically. There might be a glow as the reaction happens. You end up with a hard, black, solid mass. This is iron sulfide, FeS, a compound.
A new substance. Black, not gray, and yellow bits.
Totally new substance. Now, test its properties. Bring the magnet near this black mass.
Does the iron still stick?
Nope, the magnet has no effect. The iron is no longer present as elemental iron. It's chemically bonded within the iron sulfide compound. And the compound itself isn't magnetic in the same way.
Wow. Okay.
Now try adding carbon disulfide to the black iron sulfide powder.
Does the sulfur dissolve out?
No. The black mass doesn't dissolve. The sulfur is chemically locked into the compound. It no longer has the property of dissolving in carbon disulfide. The original properties of both iron and sulfur are completely lost because they've chemically combined to form something new.
That's a perfect illustration. Mixture keeps properties, compound loses them and gets new ones. Okay, this brings up another point. Mixtures. How do they actually look? Can we always see the different parts? Or can they trick us?
That's a great question, and it leads to another important classification within mixtures. We divide them into homogeneous mixtures and heterogeneous mixtures, based on how uniformly the components are spread out.
Homogeneous and heterogeneous. Okay, what's homogeneous?
A homogeneous mixture is one where the components, the different substances, are uniformly distributed throughout the entire mixture. So uniformly, in fact, that you cannot distinguish the different parts even with a powerful microscope. It looks like a single substance.
Like the saltwater example. Once the salt dissolves, it looks just like water.
Exactly. Salt solution, sugar solution, vinegar, which is acetic acid dissolved in water, clean air. These are all homogeneous mixtures. They have the same composition and properties throughout any sample you take.
So are you saying that some things we might even think are pure substances are actually these homogeneous mixtures? Like what about tap water? Or milk?
Absolutely.
Yeah.
That's often the case. Tap water isn't pure HO. It contains dissolved minerals and salts, maybe tiny amounts of chlorine. You can't see them, so it's homogeneous, but it's definitely a mixture.
Huh. And milk?
Milk is a classic example of a complex, homogeneous mixture. Technically a colloid, but it appears uniform. It's mostly water, but it has fats, proteins like casein, lactose, milk sugar, vitamins, and minerals, all dispersed evenly throughout. You can't look at milk and pick out the fat globules or the protein molecules. Other surprising examples. Honey is a homogeneous mixture of various sugars, fructose, glucose, and water. Fruit juice contains water, sugars, acids, vitamins, flavor compounds. Ice cream is a complex mix of ice crystals, air bubbles, fat globules, and sugar solution. Ink, like the black ink we mentioned, is usually a homogeneous mixture of several dyes dissolved in a solvent. Even alloys, which are mixtures of metals, are often homogeneous, like brass, copper and zinc, or bronze, copper and tin, maybe zinc. The metals are mixed so thoroughly, often melted together, that they form a uniform solid solution.
Wow, okay. So many everyday things are actually homogeneous mixtures hiding in plain sight. What about the other kind then, heterogeneous?
Heterogeneous mixtures are the opposite. Here the components are not uniformly distributed. You can often see the different parts or the composition varies from one point to another.
So these are the ones where you can clearly tell it's a mix.
Often, yes. Think about soil. It's got bits of rock, sand, clay, organic matter. It looks different depending on where you grab a handful. Sand and water, the sand settles, clearly separate from the water. Oil and water, they form distinct layers because they don't mix.
The classic salad dressing separation.
Exactly. Or simpler things like mixing rice and lentils. You can easily see the individual grains. A chocolate chip cookie is a heterogeneous mixture, cookie dough, and chocolate chips are not uniformly spread at the molecular level.
Okay, that distinction makes a lot of sense. Homogeneous looks the same throughout. Heterogeneous, you can see the different bits or layers. This is a great map of, well, of stuff. But why is knowing all this, especially about mixtures, so important? Why is separating them such a big deal outside of a chemistry class?
Oh, the need for separation is incredibly practical and absolutely vital in countless ways in our daily lives and in industry. There are three main reasons we separate mixtures.
Okay, what's reason one?
First, to obtain useful substances. Think about getting salt from seawater. Seawater is a mixture, mostly salt and water. We need the salt, so we have to separate it from the water on a massive scale. Or extracting metals like iron or aluminum from their ores, those ores are mixtures found in the earth.
Right, getting the valuable component out. Makes sense. Reason two.
Second, to remove undesirable or harmful substances. This is something you probably do without thinking about it. When you pick small stones or bits of husk out of rice or lentils before cooking, you're separating an undesirable component from the useful one. Purifying drinking water involves removing harmful bacteria, suspended solids, and unwanted chemicals, all separation processes.
Health and safety, basically. Got it. And the third reason.
Third, and this is crucial for science, medicine, and technology, is to obtain completely pure substances for specific uses. For example, the water used to make medicines or solutions for laboratory experiments needs to be extremely pure distilled or deionized water. Any impurities, even tiny amounts, could interfere with the medicine's effectiveness or ruin a sensitive experiment. Manufacturing computer chips requires ultra-pure silicon.
So precision requires purity. Useful stuff, safety, and purity. Those are big drivers. Okay, if separating mixtures is so important and there are so many kinds of mixtures, how do we choose the right way to separate them? Seems like there could be dozens of methods.
There are quite a few methods, you're right, and choosing the right one is key. It's not random, it's based on a fundamental principle. The separation technique you choose depends entirely on the type of mixture you have. Solid, 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 liquid, 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 etc. And crucially, on the differences in the physical properties of its components.
Ah, the properties again, like what kind of properties?
Things like particle size, shape, color, if you can see the difference. Density, does one thing float and another sink? Melting point and boiling point differences. Solubility, does one component dissolve in a particular liquid while the other doesn't? Magnetic properties, is one component attracted to a magnet? Or even the ability to sublime, to turn directly from a solid to a gas. You exploit these differences to pull the mixture apart.
It's like finding the weakness, the difference you can exploit. Okay, let's dive into some of these techniques. What about separating solids mixed with other solids?
Right, for solid-solid mixtures, we have several common methods. The simplest is hand picking.
Like picking stones out of rice, you mentioned.
Exactly. If the components are visibly different in size or color, and you don't have a huge amount, you can just pick them apart by hand. Obviously, it's slow and tedious for large quantities.
Okay, hand picking for visible differences. What else?
Winnowing. This is an age-old technique, especially in agriculture. It uses wind or a current of air to separate lighter solid particles from heavier ones. Think of farmers tossing grain in the air. The lighter husk blows away while the heavier grain falls down.
Clever use of air and density.
Then there's magnetic separation. This works brilliantly if and only if one of the components is magnetic, like iron, nickel, or cobalt. If you have a mixture of iron filings and sulfur powder, or iron filings and sand, you just run a magnet through it and the iron jumps onto the magnet, leaving the non-magnetic stuff behind.
Simple and effective if you have iron involved.
Gravity separation is another one, often used with water. If you have two insoluble solids with significantly different densities, like sand and sawdust, you can put the mixture in water. The denser sand will sink, while the lighter sawdust will float. Then you can skim the sawdust off and pour the water away from the sand.
Using water to exploit density differences. Neat.
Then there's a really interesting one. Sublimation. Remember we said some solids can turn directly into a gas when heated, skipping the liquid phase?
Right, like dry ice.
Dry ice. Solid COers does that, yes. Other common substances that sublime are iodine, camphor, naphthalene, mothballs, and ammonium chloride. So if you have a mixture where one component sublimes and the other doesn't, You can separate them by heating.
How does that work exactly?
Take a mixture of common salt, sodium chloride, and ammonium chloride. Salt doesn't sublime, but ammonium chloride does. If you heat this mixture gently in an open dish, the ammonium chloride will turn into vapor and drift away. Or, more cleverly, you can heat it in a dish covered with an inverted funnel. The ammonium chloride vapor rises, hits the cooler surface of the funnel, and turns back into a solid deposition, coating the inside of the funnel. The salt just stays behind in the dish.
You heat it, one turns to gas, you cool the gas elsewhere to get it back as a solid. Very cool. Any others for solid-solid?
One more common one is the solvent extraction method. This relies on solubility differences. If you have a mixture where one solid dissolves in a particular solvent, like water, alcohol, etc., and the other doesn't, you can use that solvent to separate them.
Like the sand and salt example again.
Exactly. Mix sand and salt, add water, the salt dissolves, the sand doesn't. Then you can filter the mixture, the sand stays on the filter paper, and the salt solution passes through. Then you just evaporate the water from the salt solution to get the solid salt back. You use the solvent water to extract the salt from the sand.
Okay, hand-picking, winnowing, magnetic, gravity, sublimation, solvent extraction. That's a good toolkit for solid mixtures. What about separating solids from liquids?
For solid-liquid mixtures, the method really depends on whether the solid is dissolved, making a homogeneous solution, or just suspended and insoluble, a heterogeneous mixture.
Let's start with the insoluble ones, the heterogeneous mixtures, like sand and water.
Okay, for insoluble solids and liquids, if the solid particles are heavy and settle down quickly, you can use sedimentation and decantation. Sedimentation just means letting the solid settle to the bottom. That settled layer is called the sediment. Decantation is then carefully pouring off the clear liquid, called the supernatant liquid, without disturbing the sediment.
Like when you wash rice, let the cloudy stuff settle and pour off the water.
Precisely. It's quick, but maybe not perfectly clean separation. For a better separation of finer insoluble solids, you use filtration.
Like making coffee with filter paper.
Exactly the same principle. You pass the mixture through a filter medium, usually filter paper in the lab. The liquid part, called the filtrate, passes through the tiny pores of the filter paper. The solid particles are too large to pass through, so they get trapped on the filter paper. This trapped solid is called the residue. It's great for separating things like chalk powder from water or tea leaves from brewed tea.
Okay, sedimentation, decantation for coarse stuff, filtration for finer insoluble solids. Now, what if the solid is soluble, like salt dissolved in water, a homogeneous solution? How do you get the solid back then?
For soluble solids and liquids, the most common method is evaporation. You simply heat the solution. The liquid solvent turns into vapor and escapes into the air, leaving the dissolved solid behind. This is how salt is commercially obtained from seawater in large evaporation ponds.
Just heat it till the liquid's gone. But what if you want to keep the liquid too?
Good point. Evaporation recovers the solid, but you lose the liquid solvent. If you want to recover both the dissolved solid and the pure liquid solvent, you need to use distillation.
Distillation? How is that different from just boiling it away?
Distillation involves two steps: evaporation followed by condensation. You heat the solution in a distillation flask. The liquid solvent evaporates, turning into vapor. But instead of letting the vapor escape, you direct it into a cooled tube called a condenser.
Okay, so you trap the vapor.
Right. As the hot vapor passes through the cold condenser, it cools down and condenses back into a pure liquid. This pure liquid, called the distillate, is collected in a separate container. The dissolved solid, which doesn't evaporate, remains behind in the original flask.
So you get the pure liquid in one container and the solid left in the other.
Exactly. It's perfect for purifying liquids. For example, purifying tap water, which contains dissolved salts, to get pure distilled water for use in labs or car batteries.
Evaporation for just the solid, distillation for both solid and pure liquid. Got it. Now what about liquids mixed with other liquids?
Okay, liquid-liquid mixtures. Again, it depends if they mix or not. Do they dissolve in each other, miscible, or form separate layers, immiscible?
Let's do miscible first, liquids that dissolve completely, like alcohol and water. How do you separate those?
For miscible liquids, provided they have different boiling points, the technique is fractional distillation. It's similar to simple distillation, but more sophisticated, designed to separate liquids whose boiling points are relatively close together, usually needs a difference of at least 5 degrees Celsius, ideally more.
Fractional distillation. How does it work better than simple distillation for this?
It uses a special piece of equipment called a fractionating column, placed between the distillation flask and the condenser. This column is often filled with glass beads, rings, or Has a special design that provides a large surface area.
Why the large surface area?
As the mixture boils, both liquids vaporize, but the vapor will be richer in the component with the lower boiling point. As this mixed vapor rises up the fractionating column, it undergoes repeated cycles of condensation and re-evaporation. Each cycle further enriches the vapor in the more volatile component, the one with the lower boiling point.
So it gradually purifies the vapor as it goes up.
Exactly. By the time the vapor reaches the top of the column and enters the condenser, it's essentially pure vapor of the lower boiling liquid. That condenses and is collected. The higher boiling liquid tends to condense and drip back down the column.
So you collect the lower boiling one first, like separating alcohol, boils around at 78 degrees Cc from water, boils at 100 degrees C.
Perfect example. You'd collect the almost pure alcohol first. This technique is hugely important industrially. It's the primary method used in oil refineries to separate crude oil, which is a complex mixture of many different hydrocarbons into useful fractions like gasoline, petrol, kerosene, diesel fuel, lubricating oils, all based on their different boiling ranges.
Wow. Fractional distillation powers the world, basically. Okay, that's for miscible liquids. What about immiscible liquids, the ones that don't mix, like oil and water? That seems easier.
It usually is. For immiscible liquids that form separate layers, because they have different densities, we use a simple piece of glassware called a separating funnel.
What does that look like?
It's basically a pear-shaped funnel with a stopper at the top and a tap, stopcock, at the bottom stem. You pour the mixture of immiscible liquids into the funnel, put the stopper in, maybe give it a gentle shake, and then let it stand undisturbed.
And the layers form?
Yes. The liquids will separate into distinct layers based on their density, with the denser liquid settling at the bottom and the less dense liquid floating on top.
So oil would be on top of water?
Usually yes, because most oils are less dense than water. Kerosene and petrol also float on water. Once the layers are clearly separated, you carefully open the cap of the bottom and let the lower, denser layer drain out into a beaker. You close the tap just as the interface between the two layers reaches it. Then you can drain the upper layer into a different container.
Simple, visual, effective.
Nice. You also mentioned gas-liquid mixtures briefly.
Yeah, just quickly. If you have a gas dissolved in a liquid, like the air dissolved in drinking water, simply heating the liquid usually decreases the solubility of the gas, causing it to bubble out and escape. That's why boiled water tastes flat. The dissolved air that contributes to its taste has been driven off by the heat.
Makes sense.
Yeah.
Okay, before we move to the really advanced stuff, you had a great example that pulls several of these methods together, like a separation puzzle. The sand, sawdust, and salt mixture.
Ah, yes, that's a good one to show how you combine techniques. So you have a mixture of sand, sawdust, and common salt. 3 solids. How do you get all 3 separated?
Okay, Salt dissolves in water, the others don't. Good start. So, first step. Add water to the mixture and stir well. What happens?
The salt dissolves in the water. The sand is insoluble and heavy, so it should sink. The sawdust is also insoluble, but light, so it should float.
Perfect. So now you have sand at the bottom, salt dissolved in water, and sawdust floating on top. What next?
Maybe carefully scoop or pour off the water with the sawdust.
You could decant, yes. Pour off the salty water containing the floating sawdust, leaving the sand behind in the first container. So sand is separated, though it's wet.
Okay, sand is done. Now we have salty water with sawdust floating in it. Filter it.
Good idea. Filter that mixture. The sawdust particles are solid and will get trapped on the filter paper. The salt solution, being a true solution, will pass through the filter paper as the filtrate.
Right. So now sawdust is separated, trapped on the filter paper.
Correct. Sawdust is done. What are you left with?
Just the salty water, the filtrate.
And how do you get the solid salt back from the water?
Evaporation. Heat the filtrate, the water boils off, and the salt crystals are left behind.
Exactly. Evaporation recovers the salt. So by combining, dissolving in a solvent, water, decantation, filtration, and evaporation, you've managed to separate all 3 components of the original solid mixture. It shows how you often need a sequence of steps based on different properties.
That's a brilliant example. Okay, we've covered a lot of ground with these separation techniques, but what about those really, really tricky mixtures where the components are super similar, maybe present in tiny amounts, and things like distillation or filtration just won't cut it?
Now you're getting into the realm where we need more powerful, more sensitive techniques. And the star player here, especially in modern chemistry and biology, is chromatography.
Chromatography. Sounds fancy. What is it?
It is a very powerful set of techniques, yeah. It's particularly useful for separating complex mixtures, where the components have very similar chemical and physical properties, making them hard to separate otherwise. Think about separating the different colored pigments in a leaf, or the different amino acids in a protein sample, or, like you said, the different colored dyes in ink.
Where does the name come from? Chroma sounds like color.
It does. The name literally comes from the Greek words chroma, meaning color, and graphin, meaning to write. So color writing. That's because the technique was first developed and used to separate colored substances like plant pigments. But don't let the name fool you nowadays. Chromatography is used extensively to separate colorless substances too. The principle works regardless of color.
Okay, so how does this color writing or substance writing actually work? What's the basic idea behind it?
The fundamental principle behind all types of chromatography is based on differential distribution. You have two phases. A stationary phase, which stays put. It could be a solid like filter paper or silica gel packed in a column, or even a liquid coated onto a solid. And a mobile phase, which moves. This is usually a liquid solvent or a gas that flows over or through the stationary phase.
Stationary phase stays, mobile phase moves. Got it.
Now, you introduce your mixture into this system. The components of the mixture get carried along by the moving mobile phase. But they also interact with the stationary phase. They might stick to it or absorb onto it to varying degrees.
So some stick more, some stick less.
Exactly. Components that interact weakly with the stationary phase or are more soluble in a mobile phase will spend more time moving along with the mobile phase and travel faster. Components that interact strongly with the stationary phase will be held back, slowed down, and travel slower.
So it's like a race, but the track, stationary phase, is sticky, and different runners' components get stuck for different amounts of time.
That's a great analogy. Because they travel at different speeds, they gradually separate out from each other as the mobile phase moves along. Over time or distance, you get distinct bands or spots corresponding to the separated components.
Can you give us a simple visual example of how this looks in practice?
Sure. The simplest type to visualize is paper chromatography. Remember the ink example?
Yeah, the black ink separating into colors.
Right. Imagine you take a strip of filter paper. That's your stationary phase. Near the bottom edge, you put a small spot of Drussic ink, your mixture. Then you hang the paper strip so that the very bottom edge dips into a shallow layer of a suitable solvent, like water or alcohol, that's your mobile phase, in a beaker, making sure the ink spot itself is above the solvent level.
Okay, paper dipping into the solvent below the spot.
Now the solvent starts to move up the paper by capillary action, just like water soaking up a paper towel. When the solvent front reaches the ink spot, it starts to dissolve the different dyes in the ink.
And carries them up the paper.
Yes, but at different rates. The dyes that are more soluble in the solvent and less absorbed, less sticky, to the paper fibers will travel farther up the paper along with the solvent. The dyes that are less soluble or more strongly absorbed will lag behind, moving slower.
So the single black spot separates out
into a series of distinct colored spots or bands at different heights on the paper. You might see blue, red, yellow spots appearing at different distances from the original spot. It visually reveals the different components that were mixed together to make the black ink.
That's fantastic. A really clear way to see separation based on subtle differences. What are the big advantages of using chromatography? Why is it so important?
It has several major advantages. One, it can work with very small quantities of a mixture. You only need a tiny spot of ink or a very small sample of blood, for example. This is crucial in fields like forensics or medical testing, where samples might be limited.
Okay, where's the tiny amounts?
Two, it's incredibly powerful at separating components that have very similar physical and chemical properties. Things that might have almost identical boiling points, making fractional distillation difficult, can often be separated easily by chromatography because their interaction with the stationary phase might be just slightly different.
So it's highly sensitive to small differences.
Extremely. And third, chromatography isn't just for separation, it's also used for identification. By comparing how far a component travels under specific conditions, we call this its retention factor, or RF value, to known standards, you can often identify what the substance is. So it separates and helps identify.
Separation and identification in one technique. That's powerful. Where do we see chromatography being used in the real world? What are its key applications?
Oh, it's everywhere, really, behind the scenes. It's used to separate pigments from natural sources, like getting different colors from plants. Critically, it's used in pathological labs to separate drugs from blood samples. If doctors suspect poisoning or need to monitor drug levels in a patient, chromatography is often the tool used to detect and measure those specific substances in the blood or urine.
Huge for medicine and forensics, then.
Absolutely. It's also widely used in the chemical industry, for instance, to separate different colors from dyes during manufacturing or quality control, to ensure food safety by detecting contaminants or additives, and in environmental monitoring to identify pollutants in water or air samples. It's a truly indispensable analytical tool in modern science and technology.
Well, we have certainly covered a lot today. It's been quite a journey, hasn't it? We started with just thinking about all the stuff around us, then dove into the fundamental ideas of elements, those basic building blocks and compounds, where elements combine in totally new, sometimes surprising ways.
With those completely transformed properties.
Exactly. And then we explored mixtures where substances just blend together without changing their core identities. And the second half, understanding why we need to separate these mixtures for useful materials, for safety, for purity, and how we do it, using all those clever techniques based on physical properties.
From simple hand-picking and filtering right up to sophisticated distillation and chromatography?
Right. It really feels like understanding these basic concepts, element, compound, mixture, and the principles of separation gives you a whole new lens.
Yeah.
A powerful way to look at the world and see the kind of hidden chemical puzzles that are literally everywhere.
It absolutely does. So maybe here's a final thought to take away. The next time you pour yourself a glass of milk, or maybe look at a rock, or even just take a breath of fresh air,
Yeah.
pause for a second.
Yeah.
Think about what you've learned. What hidden mixtures or pure substances might you be interacting with right at that moment?
Right.
And just for fun, what clever ways, based on their potential properties, could you imagine separating them if you had to? The world really is this vast, dynamic chemical laboratory, constantly mixing and sometimes separating, and you now have a much deeper insight into how it all works.